The sliding filament theory states that muscle contraction is caused by the shortening of sarcomeres within a muscle fiber. Muscles are made up of fascicles containing muscle fibers, which are considered the individual cells of muscle tissue. These muscle fibers contain myofibrils, which are bundles of the protein filaments responsible for muscle contraction. These filaments are known as actin, myosin, and titin, and they form contractile units known as sarcomeres, which are separated from one another by Z-discs. Contraction within these sarcomeres is caused by a reaction which begins at the neuromuscular junction between a motor neuron and a muscle fiber. After a nervous impulse reaches the end of an axon, it stimulates the release of calcium ions from voltage-gated calcium channels. The calcium content in the axon terminal prompts synaptic vesicles to fuse with the axon membrane and release their contents into the synaptic cleft via exocytosis. These vesicles contain a neurotransmitter known as acetylcholine, which, once released, diffuses across the synaptic cleft and binds to the ACH receptors on the motor plate of the sarcolemma. Once this happens, ligand-gated ion channels open, allowing for sodium ions to diffuse in and potassium ions to diffuse out. The amount of sodium ions that enter is greater than the amount of potassium ions that exit, resulting in a depolarization of the membrane known as an end-plate potential. This end-plate potential generates an action potential, which is propagated down the sarcolemma, eventually reaching the T-tubules, which help transport it deep into the cell. The action potential moving down the T-tubules triggers the release of calcium from the terminal cisternae of the sarcoplasmic reticulum. Once calcium is released into the cell, it binds to the troponin located on actin filaments. Calcium-activated troponin changes shape, moving the tropomyosin away and exposing the active sites of the actin. The myosin head, which is in a cocked high-energy position powered by the energy released from the hydrolysis of ATP to ADP and phosphate, binds to the active site of the actin. This binding step is called cross-bridge formation. The myosin head pivots and changes to a low-energy bent state as it does so, causing the actin filament bonded to it to slide towards the center of the sarcomere. As this happens, the ADP and phosphorus are released from the myosin heads. When a new ATP molecule comes and binds to the myosin head, it detaches from the actin, returning to its initial position. When the ATP is hydrolyzed into ADP and phosphorus, the energy released causes the myosin head to cock into position again, ready to repeat the cycle. The repeating cycle ends when the action potential ends and the calcium ions are returned to the sarcoplasmic reticulum by active transport. The lack of calcium causes the re-establishment of the tropomyosin blockade, effectively preventing cross-bridge activity and encouraging relaxation of the muscle.